Okay, I think we are ready to get started. Good morning. Thank you everybody for joining us today for this Google Plus on-air Hangout, Security Strategies for Internet of Things Systems from Devices to the Cloud, presented by Mentor Graphics Embedded Software. My name is Matt Radishonsky. I'm on the Mentor Embedded Marketing team, and I'll be your host today. My colleague Kamran Shah will be moderating this panel discussion. We'd like this to be as interactive as possible, so please feel free to use the commenting section just below the live YouTube stream to enter in any questions you have, and we will do our best to address them in real time. We've also allocated some Q&A time at the end of the presentation as well, if you'd prefer to save your question for that. Following this question, the YouTube recording of this live panel will be available on the event page that you're at now, and we will also post a link to the slides that we share today. Moderating this panel will be Kamran Shah. Kamran is the Director of Marketing for Mentor Graphics Embedded Software. He's held multiple technical roles that span across marketing, product management, research and development, and has been awarded 18 patents. Kamran graduated from the Texas A&M University in 1999 with a degree in computer engineering. Kamran will be joined by Felix Baum, James Wickett, Andrew Caples, and Karthik Gotsquad. Without further ado, Kamran, I will pass the mic over to you, turn my microphone off, and we can get started.
Great, thanks, Matt. I appreciate the introduction. So I'll introduce other members as we go through the Hangout, just so we can get into the meat of the discussion and keep going. So what really spurred me to schedule this discussion was I attended a number of shows, CES, Embedded World, eLive, and everybody's talking about the Internet of Things. But really, one of the important things to everybody's really talking about the Internet of Things. One of the things that came up in some of the discussions I had was there was some concern about what's the impact of security to the Internet of Things. And that's really why we put this group together. And when somebody talks about Internet of Things, really I think of it as the introduction of connectivity and intelligence in a device as all of us are used to around the home, office, and workplace. And so I'll share some of these concepts in a couple of slides just to do a little bit of frame setting, and then we'll hand it off to the other guys on the panel that'll go into more of the details. So really the Internet of Things isn't really about a specific industry. It spans all these different industries. So you have sensors on bridges that monitor vibrations, and that really helps us do better preventative maintenance and monitoring. There was a recent announcement with Bosch and Siemens of home appliances that will actually monitor energy prices. So your washing machine will actually run when energy prices are the lowest. And you just say, hey, run during the day. I really don't care when. You're just washing my clothes. And that's all encompassed in the Internet of Things. But all of these really have a common architecture to them. So when I look at it, you have some devices that connect over Bluetooth or Bluetooth Low Energy to a phone, and then the phone connects up to a service, whether it's in the cloud or a data center that somebody's hosting. Another mode is you have devices connecting over Wi-Fi, and those will either you connect through a router or gateway or just bypass them and go straight to a service in the cloud. And really, it's that bidirectional data interchange that defines the Internet of Things. And when we talk about security for the Internet of Things, we really need to look at that entire system. So just having a secure web server or database isn't enough. You have to have the device be secure. You have to have the transmission of the data through encryption or cryptography be secure. And then the web services themselves also have to be secure and have a mechanism to do the permissioning, the authorization, and validation. So this really is an interesting topic because it isn't just securing one thing, it's securing that entire ecosystem of the Internet of Things. And so the panel we've kind of put together spans people with embedded device development expertise, security expertise, web service expertise, so we can kind of get a nice feel for all these different pieces of it. And one of the interesting things that always comes up is people are like, well, does security really matter for the Internet of Things? And I would say it really depends on the device, right? So if I have a activity monitoring device around my wrist, yeah, somebody gets at that data. I'm not that worried about it. But then if you're looking at a clinical medical application where you're introducing connectivity, well, the reliability and certification requirements are really stringent. So how do you add in connectivity in a mixed criticality environment is very different than adding that into a consumer device where some of those things may not be as prevalent. But even in consumer devices, you have concerns of credit card information or other sensitive information that you don't want to make accessible to other people. So it really does become something that you want to be aware of, and that's what this panel discussion is about. But what you end up doing will really be determined by what is your end application and device. So that's something I'm hoping some of the Q&A that you guys bring up will help us go into. So what I want to start with is Andrew Caples. He's the Senior Product Manager for the Nucleus RTOS. And we'll start on the device side and then move up into the device connectivity and then the cloud side during this panel discussion. So Andrew, I just wanted you to take some time sharing what you think are some of the software-related security issues that people will need to consider when they're adding connectivity into devices to be part of this Internet of Things ecosystem.
Okay, Kamran, thanks very much. So I put together a few slides here. Hopefully the audience will be able to see these. So these slides are actually put together just to really get the conversation going here. I think it's healthy or productive to start with a conversation on, security versus reliability when it comes to Internet of Things. So from some vantage points, there's a clear distinction between reliability and security. In simple terms, of course, reliability deals with the internal functioning of the system, while security deals with the external attacks of possible intruders. If the system does not function, per the spec or design goal, well, it's considered a bug. So there's a clear definition, of what a bug is, right? Deviation between the application and the spec. However, for security, it isn't so easy to specify all the ways an application might be exploited. So kind of, bundling that into a spec isn't really that straightforward. And without a spec, of course, topics such as coverage and completeness of testing can be somewhat nebulous. And it does make the testing much more harder. So if you look at it, negative versus a positive goal, security is hard because it is a negative goal, and a negative goal, just inherently is harder. What does that mean? Well, in the reliability domain, right? If there's a 1% chance of something going wrong, that could be okay. That could meet the design spec. I'm not suggesting everybody design their products with 1% chance of things going wrong. Just making a point. However, in the security domain, if the probability distribution really isn't in our control, right? If there's a 1% chance of failure, well, the adversary is going to focus on making that 1% happen all the time. So the point is, malicious third parties really control the probability distribution when it comes to security. So for IoT devices, there are many different aspects to security, areas that can be focused on, ensure the code, cannot be modified by a malicious attacker, ensure software upgrades are conducted safely. You don't want to inject malicious code, and ensure the device is robust enough to handle network attacks. So with that, what are some of the threats, faced by IoT devices? Well, certainly, boot time threats. There's a need for trust and authentication. The trust, there needs to be some way to ensure that the boot code and the OS have not maliciously been tampered with. Some sort of authentication is needed to ensure software updates and upgrades, and the software that's actually loaded is verified to be authentic. In the runtime arena, there are runtime threats, and for the user space, there's a need to create protected areas where software can be partitioned and protected. Areas that offer isolation. Yet, these areas, need to be real time and lightweight. and then networking, of course, because in the Internet of Things, everything is connected. The device needs to be able to be robust enough to be able to handle any sort of IP attack or cybersecurity threat. So there's this concept of the root of trust. If we look at the boot time threats, so essentially, a device certainly, the initial line of defense is controlling access, of course. But once the device is booted, there is a need to prevent anything that's not trusted. We certainly don't want that to be used on the system to boot the system. And then when you go from boot to the operating system, you want to prevent any untrusted OS from launching, and of course any application being launched by the OS. And then during execution, you want to be able to prevent attack. So establishing that software-hardware trust, hardware to boot ROM to operating system, and operating system to application. So when it comes to booting an operating system, or actually a binary image on an embedded IoT device, certainly the way devices function today, much of that code resides in Flash, and you're going to copy to RAM. Well, before that copy is made, a couple of questions, important questions, should be asked. Can you verify what you're about to copy? Did it originate from the OEM? Has it been modified in any way? And these are just some initial intuitive questions that one would ask to ensure that there is no unauthorized code being entered into the system. So how can we do that? Well, essentially, boot time authentication strategy can include the concept of a private key and a public key, where the OEM has a private key, and for signal generation, in this case, I'll use the Nucleus RTOS as an example because that's the RTOS I'm the product manager for. There can be a hashing function that generates a code, and using a private key, a signature can be generated, and that signature can be protected in some isolated memory that's not accessible. So any subsequent booting of the system would be verified against that secret signature, and the system would only be allowed to be boot if that signature actually matched. So from a boot time authentication strategy perspective, the sequence would be, the unsigned image, such as Nucleus RTOS, being loaded. It would go through this hashing function, and the secret signature would also be decrypted using the public key, and only if there's a match between the decrypted signature and the Nucleus unsigned that had gone through the hashing function would the process be allowed and the system be allowed to boot. So these are strategies that can actually be deployed to ensure the authentication and the integrity of the code that's being used. Now this can actually transcend the booting, right? So we talked about establishing a root of trust, and that really is important to establish that root across the entire spectrum of software. So from your first stage bootloader, having a signature and a crypto key that can be used to validate your second stage bootloader, which can subsequently be used to validate your operating system, and of course any applications that you want to load. Now, what we're seeing is a trend by hardware manufacturers to actually include capabilities within their hardware to help facilitate establishing this root of trust. ARM is a perfect example. You've got ARM TrustZone that can be used for crypto key storage, signature generation, signature load, and of course loading the OS and the apps. You're also seeing other examples like from Freescale, the IDMX6, where you have the high assurance boot. These are services, for the ROM to authenticate software that executes immediately, after the boot code is loaded. It uses digital signatures The code can actually be loaded from external memory devices, such as USB or MMC card, but also from NAND flash and double EEPROM. And it works very similar to what I explained using encryption, RSA algorithms with encryption, including AES 128. And the way it would work is a digital signature would be established using a hashing function to generate a code that could be encrypted using a private key. And then any software that's subsequently loaded would go through the same hashing function and be compared to that code that was decrypted and only allowed to run if it was validated and verified to be authentic. From a user space perspective, just looking at it from a high level, when you're doing software upgrades or uploads, there is a need to go through the root of trust, but additionally, space partitioning provides a vehicle by which software can be protected from other software. And there's different ways to do this. We see with a general purpose operating system, some heavyweight space partitioning that includes virtual memory. For IoT, where you're going to have limited resources, a lot of IoT devices will be based on low-cost ARM processors with limited system resources and maybe MPUs. You're still can benefit from space partitioning, in which subsystems can be isolated from other subsystems, and so the entire system can have an added degree of security and reliability with the prevention of subsystems taking down the stuff. Networking threats, of course, with IoT, this is becoming more and more prevalent. There's all sorts of networking threats out there, of course. There's the TCP/IP LAN attacks, where you've got, as an example, identical source and destination IP addresses, or packets with identical source and destination TCP ports, which, of course, should never be the case. You also have, attacks using fragmented packets, where the device is overwhelmed with packets but never receives all the packets, or attacks where there's an impossible packet header field combination. For example, the don't fragment bit is highlighted in addition to the more fragmented bit, which should never be the case. So devices should undergo thorough testing to ensure they can handle storms and users and grammar issues and other types of known vulnerabilities. And lastly, just to put a plug in for Nucleus, that's again the operating system I represent. So it's full featured, and of course has a IoT networking stack and lots of connectivity and security. So with that, Kamran, I'll hand it back to you.
Thanks, Andrew. So there's a couple of questions that came in on the comments, and I had one as well as you're going through this. So one of the questions somebody posed was, so what are you supposed to do when the key doesn't match, the authentication doesn't actually match? So what's the next step from an application standpoint?
Well, there's many different ways in which that can be handled. One way is you can have a different vehicle in which you can boot up the system safely. So as an example, you can use an out-of-band booting mechanism, maybe USB, if the keys do not match and for some reason the system is not able to boot. You can have a protected way to boot that's out-of-band in order to reboot the system.
Okay. So the other thing, with the Internet of Things, there are a lot of varieties of classes of devices, right? You go from 32-bit microcontrollers to multi-core processors to heterogeneous architectures. So when you have a limited device like a 32-bit microcontroller that's now introducing a lot of capability with connectivity at a low price point, how does that impact your security kind of strategy?
Sure. No, that's a very good question. I mean, when I think of the Internet of Things, I'm thinking of IoT devices that are built on inexpensive, low power processors. Many of them will be ARM based, lots of low cost wireless connectivity. Of course, all sorts of IPv6 and middleware. and each device is actually, a distributed computing node capable of making decisions on its own. So there's a lot of middleware and a lot of complexity. But if you look at some of the MCUs out there, like the TIVA, they can get as low as 256K bytes of memory, or the Freescale Kinetis or ST Micros, with 512. So you're really packing a lot of of software, middleware, and complexity in very limited, tight spaces. So, but there's a need not to compromise on security. So, we've gone through a lot of great lengths to, of course, parse down the operating system and the middleware. Case in point, OpenSSL, which provides a lot of security capability. We've introduced a replacement CIASO, which essentially provides the same cipher crypto box as OpenSSL, yet it's about 20 times smaller than OpenSSL. So, supports client server, list of supported, ciphers is very long, key and certificate generation, online security status protocol. So a lot of capability, yet in a very, very tight footprint. So for these type of IoT devices with limited resources, you don't have to compromise on security.
Okay, well, that's good. That's good to know. Another thing you did mention in your presentation was, hardware-based security implementations as well. So at this point, I'll kind of switch over to Felix to talk about what is the hardware and software complement that semiconductors are providing. And one of those that we hear about a lot in the news today is ARM TrustZone. So Felix is actually our senior product manager for our intermittent hypervisor. So I'll ask him to talk a little bit about ARM TrustZone capabilities like it that we can take advantage of.
Thank you, Cameron. Yes, I would like to take a step back and explain for a second that the root of trust, all of the concepts that Andrew was talking about, they all start with the hardware. As some of you probably know that to truly establish the root of trust, to truly walk through that chain that Andrew described, you have to start from the power on. From the moment you turn on the hardware is in charge, and the hardware should authenticate itself and then authenticate the initial stage of the booting process, which is a bootloader, and then go with a chain of trust and have the hardware authenticate the bootloader OS, and OS applications. Now, at the end of the day, whatever it's the keys or algorithms or all these things, you need to find a place in your device where you hide it. And in many instances, the silicon vendors would develop different technologies in the silicon to provide for hiding these keys and these algorithms. Andrew also mentioned that we have a technology right now with our ARM parts that is called ARM TrustZone. And if you can see my slides right now, what ARM TrustZone is a hardware-enabled capabilities that allow a developer to partition the IP in the silicon. You can go through your device and you can literally identify which pieces of the silicon are normal and which pieces of the silicon are secure. In the secure world, when you're running your application in a secure world, you can do everything. You can access all of the peripherals, you can touch all of the memory. Now, if you switch your chip and put it in the normal world, and you run an application in normal world, then only the pieces of IP that you establish as normal would be visible. And this is how you can go and, for example, take a piece of memory, put your keys in it, and then claim that it's a secure world. So now applications running in a normal world, such as Linux applications or an RTOS or other things, they will not be able to access that IP, access those keys. If you guys right now, the audience have cell phones, you will notice that in many cases, your cell phones today already, whatever they're iPhones or Samsung devices running Android, they probably already have these capabilities enabled. For example, you take your cell phone, you try to log into your cell phone. Well, your cell phone normally provides you with a screen that wants you to type your pins. And normally what happens on the background without you even knowing it, when you get to the screen that requires you to authenticate yourself, the device puts itself into the secure world where they read the pins, where they go validate the pins, and as soon as they validated that, yes, you're the right user, they actually allow you to get to the application, or they allow you to go to online and get access to your banking information. One thing to remember is, if you're running in a secure world, you can do a lot of things. So applications that you put in the secure world better be well tested and very very well contained to lower the amount of the amount of damage they can cause if they go bad. Now, you have to understand that each one of these cores that is based on ARM Cortex-A9 or Cortex-A15 technology has ability to run in secure world or normal world. So how does it apply to the multi-core devices? Well, this is actually one of the areas where you have to be very careful, because there are two ways you can run TrustZone configurations in a multi-core devices. You can either have each core in a multi-core device to be able to go transition from the normal world into the secure world and run your applications. But there might be a lot of thrashing. You might get into the situation where two cores want to run into the secure world accessing the same key. So what we suggest and what we've done in our implementation is, for the ARM TrustZone, what you would do is you will let all the cores run only in a normal world except one, core number 0, or you can actually configure whichever core you want to. Only one core will run secure world application and then switch back and forth between the normal and secure. All other cores will only run in a normal world, and they get to run a secure world application. That application will have to run on the initial first core that you configure for it. That way, again, you're minimizing the area of attack, making your applications to be more robust, and getting away from all these pesky timing issues that are really, really hard to debug during development. So I talked a little bit about this security enabled in the TrustZone and ability to hide things. Unfortunately, just if you use this capability from an ARM, that hardware capability, it's not enough for today's world. We've seen many customers in a multi-core world that would like to run multiple applications in a normal world. We see people that want to use secure world for secure boot, for validating DRMs, for other things. And the ARM TrustZone technology only allows, it's almost like a binary. You run either in a normal world and everything in a normal world can see each other, or you run in a secure world and everything in a secure world can see everything. So what we suggest and what we've done is we try to add a little bit additional piece of software to enhance ARM TrustZone capabilities, and we brought in virtualization in the play. With the virtualization today, if you don't even have a secure world, on devices, you would expect that you should be able to run multiple operating systems on multi-core systems. You should be able to maintain strong isolation via virtualization and run, for example, Nucleus as an RTOS next to Linux or an Android in a system. So now when you put these two concepts together, embedded virtualization and ARM TrustZone, you get into the systems that actually take best of both worlds. What you will end up with is configurations such as this, for example, where in a normal world, on my slide, you can run Linux next to RTOS on top of hypervisor. And as you can see, some of the areas on the left side of my screen, some of the areas are hidden. Your Linux application cannot see or touch your DRM encryption or secure boot algorithms. There are certain devices or certain memories that are hidden and are not mapped. So Linux cannot touch that device B or that chunk of memory where the keys are hidden. Now, if you transition your chip in a secure world on the right side of my slide, then the DRM algorithm, encryption, secure boot key management, they can see everything. All of the devices visible, they have access to all of the memories and all of the peripherals. Now, this is all, of course, is in theory, and this all, of course, in a slide deck. So how does it work in a real life? Well, in a real life today, most of you probably will develop your systems based on ARM Cortex-A9 or ARM Cortex-A15 architectures. Now, if you're lucky enough, you're probably targeting for A53, 57, but those are still sometimes in the future. So let's talk about what's available in the market today. Cortex-A9 cores have two modes of operation. There's a user mode space and the kernel mode space. If you're looking at the left top portion of the screen, what you would do then is when you try to bring in a hypervisor, secure applications, and for example, two Linux virtual machines, if you don't want to change a lot in your Linux, if you don't want to modify it a lot, what you would then do is you would run your Linux on the left side. In a normal world, you have two instances of Linux, applications running in the user space, and a kernel running, guest kernels running in the drivers in a kernel mode. And then hypervisor itself will actually be physically executing in a secure world. If you still want to have a protection, if you have to be more a little bit more robust, what you would do on ARM Cortex-A9, and again, it's on the left side of my screen at the bottom, is you would actually run a user space Linux, what we called, where both Linux instances run in a user mode. Hypervisor is now hidden and protected, running in a kernel mode space. And in a secure world, you're only executing your secure applications, and TE, which stands for Trusted Execution Environment. It's a set of APIs that are well defined, and we can go and clearly support a specific set of API to make sure that your applications is portable. Now, if you are lucky and you're using Cortex-A15 devices, such as, for example, from TI, we have OMAP 5 or Jacinto 6. Well, Cortex-A15 architecture brings in additional mode. There's a hypervisor mode. So what we do, an implementation that we've done on a hypervisor for Cortex-A15 devices, is we run hypervisor in a hypervisor mode. The Linux kernel instances, in this case, the two guests are running side by side. And in a secure world, well protected and safe, we have secure applications and TE running. Again, this is something that we have already today. We developed that technology, and if you have any questions, please feel free to come to us and we can explain to you in excruciating details how this technology comes together and works. With that, let me stop sharing my slides, and I'll go back to Cameron to find out if there are any questions for me.
Yeah, so one thing, we had one question, Felix, that talked about you know, right now you've been talking about ARM TrustZone, but there's other protection management mechanisms in x86 architectures. So is this approach limited to ARM architectures, or what are other options people have?
In x86, for example, Intel has spent a lot of time and effort in putting secure technologies in their silicon. They have TXT capabilities in their silicon. They have TMP. They have advanced random number generators. There are a lot of other technologies. Freescale with a power architecture has also developed trust architecture. I think what you'll find unique to ARM is that ARM actually went into the silicon and enabled not a separate modules, but actually they redesigned the whole core for the ARM TrustZone. They literally, the way I like to describe it, and again, I'm a software guy, is they literally went to every hardware IP block in the chip, in a SoC, and added an extra wire to be able to go and transition that particular piece of SoC to turn it on or off. That way, every single piece of IP in a hardware could function in either mode. And it's unique to ARM, and we believe that it's a really nice implementation and being able to go and secure your SoCs and your applications.
Okay, cool. So there's a couple of other questions that I think might be useful to get a little more information from you on, and that has to do with the actual access and isolation of the memory. So a number of people were commenting on, hey, well, the data is still stored in that memory, why can't somebody else access it? So could you explain a little bit about on what prevents that secure memory being accessed from other areas?
Absolutely. There are a number of different mechanisms that you can deploy. And what we've done with our implementation, for example, we set up a certain areas of memory to be able to share between the virtual machines that are running and controlled by the hypervisor versus the secure world and applications that are running in a secure world. There are different interfaces we use, for example, VirtIO. There's different ways to communicate between them. And what we've done with our design is try to optimize it for the real time. So if you're trying to take a piece of memory, take a data, and pass it, for example, into the secure world for for an application to go and authenticate or decrypt your file, you don't really have to take the whole file and slowly, surely make a hypercall, copy the whole file into the hypervisor, and have hypervisor kind of transition that file into the secure world. There are ways to set up share memory, share communications, and other passages where applications can run efficiently and maintain almost native speeds.
Okay.
Again, if you're interested to learn more, please reach out to me, and I'll be more than happy to explain it to you personally, to our viewers in excruciating details.
Cool. So there's a number of other questions that I'm actually collecting, and I'll make sure I go back to them towards the end. One thing I wanted to do right now was switch over to talk about the other side of this, which is all these IoT devices, in the end, connect up to a service or web service in the cloud, or data center, cloud, use it as a ubiquitous term. So we're sending and receiving information. So there, it's like, well, how do we know that we're connected to the right server on the other endpoint? And then how does the server know that I should even let this device send data in? Is it sending bogus data? Is the device been corrupted? We kind of went over the device corruption and security element of the data side. So Karthik is a web software engineer, and he has a lot of experience with cloud-based authentication authorization. So I'll ask Karthik go through this, and then we'll come back, by the way, at the end, and go over all the other questions you guys have posed on what about 8-bit microcontrollers and a number of other interesting things that I'll field back to Andrew and Felix. So hang on for them. They'll get some more time towards the end. Karthik, go ahead.
Hey, thanks, Kamran. On the cloud side, typically the thing that we do is most of the communication with the cloud happens via web services. There's a bunch of protocols that are being used right now, typically being HTTP, HTTPS, also newer protocols like socket-based or MQTT. For this specific podcast, I'll just talk about HTTP. But if there are questions about the others, I can answer them offline or later. So from a web service standpoint, when we have HTTP web services, there's like 3 different kinds: REST, SOAP, and RPC type of messages. In industry right now, like REST is kind of taking over, and REST is representational state transfer. Those kind of web services are taking over because it's a lot easier to consume from a consumer standpoint, and also from a web service implementation perspective, it's also pretty easy. And I actually get this question a lot between authentication and authorization, and what's the difference, and how do we implement this, and whatnot. There's really like 3 different topics here. There's identification, which is who's actually sending data; authentication, which is is this person who's sending this data, are they actually who they are; and authorization, which is are they actually allowed to do what they are. Identification and authentication kind of go hand in hand. And a lot of times authentication is always necessary, but authorization is optional. And sometimes in APIs you kind of see the authorization piece, and then but you always end up seeing like the authentication part. So in terms of mechanisms, I noticed that we had some questions on like different kinds. Right now there's like 2 kind of broad-based things, where one is user-based and the other is like device-based. And user-based, you can kind of think about it like OAuth, which is like login with Facebook or Twitter or whatever you have. And some of the benefits of that are, it's better user experience. So like consumers right now, they're kind of tired of creating newer and newer accounts, which with every single thing that you end up using, you have to create another account. It's nicer to be able to reuse an account. Like let's say you have a LinkedIn account or a Facebook account. If you're building like social applications, so let's say you're building an application that's weighing scale, right? You probably want to connect that with an account that you already have, like Facebook or something like that. From an implementation perspective, it reduces complexity, and also from a risk perspective, like you as the owner of the web services, you don't have to store additional username and passwords in your data store and worry about getting hacked and things like that. On the flip side, and this is probably more popular, is device-based, so API keys that are stored on device. Andrew touched on this a little bit, where you had a public and private key on the device, and in a lot of times you actually use API keys instead of like the OAuth thing. So the rest of this will kind of focus on that. And a lot of from an API key perspective, so the keys that you're creating are typically created in the cloud, and then they're kind of transposed to the device at the time of provisioning. And API keys are sent with each request. So HTTP is request and response based. So API keys are sent with each request to authenticate the device. So if you kind of look at this from a high level, from a sequence kind of perspective, so you have your client application, with some data that it needs to send out. It's sending it over the internet to this cloud web service. So you always end up transmitting, in this use case, via HTTPS. And HTTPS is key versus HTTP because the data that you're actually sending out people can't actually see what's inside of it. So the client transmits the data. There's the API key, which is stored in an HTTP header. And on the cloud side, the very first thing that you do is actually validate that API key. And if it's validated, then you can store the data or do whatever that specific web service is trying to do, like read or store or whatever. And then from the cloud side, you actually respond with, if everything is okay, then you respond with an HTTP 200 code. If not, you use like an HTTP like 401 response code or something, and then client takes that and if it's like in sequence, it would probably show the user a success message or an error message, or if it's happening asynchronously, you just kind of hide that. So I kind of wanted to touch on just like best practices from a cloud standpoint. So one thing you really want to do is when you're developing these web services, you really want to keep them stateless, because the importance of that is you can easily scale your requests and responses. So at one point in time, you might have like 10 devices sending you data, or you might have like thousands of devices sending you data, and you don't want to. You want your services to be able to handle that, in a scalable manner. So that's pretty important. Also, you want to decide what kind of authentication you want to use up front, whether it's like user-based or whether it's key-based, and a lot of it depends on your specific use case. Always use HTTPS because if you don't use that, then pretty much anybody over the internet can read the data that you're sending over. And in terms of API keys, the recommendation on here is to send it in an HTTP header, because if you put it in the URL or something like that, it makes different web servers can cache that, and it becomes loggable, and it's a little less secure than if you put it in an HTTP header. So with that, I know it's brief, but it just gives you like a high-level overview of how to use web services.
Okay, so one thing I'm wondering there, like in the case of web services, and I have a device. So what if what if somebody gets my key? So
Sure.
on the web service side, what do I do at that point?
So one thing that we started to see a lot of is the API keys that you get, they're only valid for a certain amount of time. So a lot of times what you'll have is, either those keys roll, or you can, on the cloud side, in your dashboard, you can say, hey, I don't trust this key anymore because typically the data that was coming from this device I thought was, in the US, but for whatever reason now this API key, this request is coming from China with that same key. Or something like that. So then you can say, disable this key.
Okay. So you can kind of have a strategy on the server side to limit device access as you come across stuff. Okay, cool. So I'll switch over a little bit from all these topics into something that's more about development approaches. So we've kind of talked about a lot of technology elements. And looking back at my career, it was interesting to me to see how agile development came from an IT and web world, and then has spanned into traditional software projects as well as embedded systems projects. And I think there's another emerging trend there that's called rugged DevOps that's being used in cloud services for developing more secure services. So I wanted James Wickett, who's a DevOps engineer and an expert in DevOps and rugged DevOps, to kind of share what that is, so all of us as embedded engineers kind of take that in and then try and think of how we could also take principles like we did with Agile, but apply rugged DevOps to embedded devices that we want to be secure. Go ahead, James.
Yeah, Kamran, thank you. You know, it's one of those things where you're facing a multi-tenant environment, which the web has been doing for a long time. Now IoT is kind of struggling or is coming up to that same standpoint, and everybody's hooking kind of web interfaces on everything. So I think it's you know, really helpful on that to be thinking through it. So, you know, rugged software started and it arose out of the need for it arose out of the need for. Are you guys able to see my slides? Okay. Okay.
Yes.
Yeah. It arose out of the need for looking at software, but in a more holistic way, because traditionally, you know, people have been battling kind of cross-site scripting and SQL injection and other web type of problems over the years. But back in 2010, there was just an outcry of saying like, okay, we need rugged software that's actually going to be repeatable, that it has limited attack surfaces. We're going to do automated configuration. We build, you know, switches and knobs and levers built in so you can control, you know, who can access things. Some of the protections Karthik was talking about, like identifying API keys that are in the wrong geography or other things like that, and be able to have, you know, real-time operations and security take, you know, make judgments on what's going on. So, and I think this is really applicable in the IoT space as well. So if you look at kind of a just here's a generic-looking IoT architecture. You know, you see the nodes and the devices are all kind of towards the bottom there. At the top, you sort of see the cloud. Depending on what cloud services or web services or backend services you're talking to, they both hook into different, like, you know, logging and visualization and monitoring, and then they span into the application space, and then they maybe would call over to your mobile or web, or maybe back to other devices and hook over that way. Each of these boxes have different threat areas and things that you know, we need to be thinking about when we're building services for the cloud and for IoT backends. And you can think about IoT you know, devices. They need to consume services just like you know, any client server architecture. And you know, backend services can be spoofed. We see threats against denial of service against IoT devices. We see weak security in multi-tenant backends that can expose information. And a lot of these end up being, you know, general web application security problems that have been documented, things like the Open Web Application Security Project. I've recently seen several IoT presentations talking about some of the same problems, and a lot of the security engineering teams out there are kind of comparing IoT now as to the web back in 1999 or 2000, you know, 2002, kind of that turn, and the security vulnerabilities are still similar. You take a lot of these industrial control systems or devices or SCADA systems, and you're hooking, you know, web front ends to them, and guess what? Those web front ends have cross-site scripting or injection attacks or other type of control things. And so, Kamran, you mentioned Agile, and you know, I think DevOps is where Agile is picking up, and rugged is an approach to DevOps and Agile that the security community has adopted. And it's sort of emphasis on testing and monitoring, treating your server infrastructure as code, thinking through things like, if DevOps is equal to, you know, culture, automation, measurement, and sharing, how does that apply to us? And this is a common structure of how people develop software for infrastructure. It's like they build it, they test, they deploy, and then they go back to dev. And then at some point, you know, whenever audit comes around or security comes around, then that is when we do security testing. But we've learned that injecting security testing earlier in the stack, either in the dev and build, and depending on what you're building, you know, these blocks may be arranged a little bit, but definitely before you deploy or shortly thereafter you deploy, you're doing your testing and security testing, and not waiting until some future thing. And that's possible through, there's Cucumber or lots of other types of testing frameworks that are available out there, but there's basically expressive testing that can, you know, hook security tools, you know, into your pipeline as you're building things. And so here's just a simple, you know, plain, easy to read attack that would be, you know, applicable to this sort of thing. And that, yeah, and it's just an approach where you're actually doing security testing inside of your dev pipeline.
Okay, cool. So I have seeing all the questions that are coming through. Whatever we can answer, we'll definitely comment on after this panel is over. But I do want to field a couple of questions. There were a couple of very similar questions that came up. One of them for Felix and Andrew has to do with lower end devices. So looking at 8-bit controllers and Cortex M0s. So one, is there any secure boot support in those? And then what about TrustZone outside of, Cortex A-class devices? So Andrew, just starting with you on what happens when you're looking at Cortex M devices, M0, M0 Plus, 8-bit microcontrollers, what is available there compared to the 32-bit microcontrollers? And then Felix, after Andrew gets done, your kind of thought on what about non-Cortex A-class devices and TrustZone?
Okay. So regarding 8-bit devices, so that's not an area that we focus on within my team, the Nucleus Real-Time Operating System team. So we focus on 32-bit devices and above. What I can say on like the Cortex M0 devices and M0 Plus, if you want to add certain types of security type features, maybe you want to create some sort of user level protection where you've got protected memory regions to isolate subsystems in a space domain type context. Typically you would have to move up to a Cortex M4 type device that offers an MPU where you can actually utilize hardware facilities to create those types of protected containers. So that's that. And Felix, I'll pass to you.
Sure. So let me kind of take a step back. First and foremost, when you trying to make your embedded devices safe, robust, secure, one of the things for you to consider is what are the areas of attacks. And let's be frank, when you're looking at the Cortex A9, A15 kind of device, you're talking about Ethernet, you're talking about a lot of peripherals, you're talking about large memory, you're talking about rich applications and full-time general-purpose operating systems versus real-time operating systems, Linux and an Android versus something like Nucleus. So you understand that area of attacks are larger. That's why some of the concepts that we talked about, they're more applicable to these larger, bigger, more powerful and not in an IoT world. Having said that, the concept of defending and protecting data, whatever it's at rest, whatever it's in use, whatever it's in transit, as applicable to the M4 devices as it is to the A9, A15 class processors. And there are capabilities like ARM TrustZone and a few others that are available to, well, first of all, known Cortex A9A devices, but also to the in x86 and Power architecture as well. There are a lot of the SoC TMP units that you can go today and purchase. There are tamper-proof devices. I mean, in the past, we've seen that you would take your embedded device, you put it in the box, you put a switch next on the box, and then you would rig your device in a such way that if someone opens the box to physically access your device and maybe take the memory out so they can dump it and copy it, your SoC will detect that, and from there on it will corrupt the memory and never boot again. So there are a lot of these capabilities that today present. What we've seen in a Cortex A class devices and newer is that all these off-the-chip, off-the-SoC capabilities are now migrating into and becoming available inside one SoC, making it harder for you to break in.
Okay, cool. So I think we have probably time for 2 more questions. So Felix, one for you. One of the things that came up for you was, so every device has a different pair of public private keys. So where is the key actually stored, and how does the device access it? Can you also use external memory to actually store this information, or how is that kind of managed?
Well, the less external stuff you use, the harder it is for someone to break in. So when you're talking about the keys and where to store them, it's up to you as a developer to determine to where you want to put it. I personally recommend it to put in an internal memory. I personally recommend it to put inside the internal memory that is bordered out and marked as a secure space. That way, less people have access to it. Having said that, there are multiple algorithms and multiple methodologies for some of them are available in an open source form of how do you go about upgrading the keys. Normally what happens is the keys are stored in the internal memory. You turn on the power, hardware gets initialized, the firmware inside the SoC that you can't even modify and only Freescale and TI, for example, as an SoC manufacturers have access to, is the one that actually gets started and executes first. It quiescens the chip, it pacifies things, it goes to that safe memory to extract the key and validate the initial first boot step. From there on, it's up to you. It's your software that gets executed in a secure world. And it's up to you to define where you want to store the key, whatever or not you want to run an algorithm or not. And the framework that some of the software vendor provides, like Mentor, for example, is sophisticated enough that allows you to determine what to do if the keys mismatch. If you're trying to boot an application and the key is invalid, what do you want to do? Do you want to still continue with the boot process and then report your device in, have it kind of say, hey, I've been stolen, please do something about it? Or do you want to crash and never boot again? So it's up to you as a developer.
Yeah, so I think that was the interesting thing I was talking about before too, was what your security strategy is really depends on your class of device, like you're saying, and you really have to be cognizant of what are the threat profiles, what's the surface attack area as well. So one last question to round it up, and we'll answer the rest of them by commenting on the thread. One other thing I'd like for you guys to do is if there's any specific topic you'd like a more in-depth session on, we'd love to get your feedback on that too. So Karthik, one of the questions that came up on the API keys was transmitting the HTTP header. Does that not put the API keys at risk?
That's actually a really good question. So typically, if you're just going to use HTTP as your protocol, then any request that you send to a server and any data in that request is compromised, because typically, like anybody sitting in the middle between you and the server, for example, can see all of that data, which is why we recommend HTTPS. So when you use HTTPS, it's the only two people that can see the data are you as the client, and then the server, because both of you guys have like the HTTP certificate in between. So in that case, you know, the API key that you send in the header or in the body or really wherever you want is protected from that standpoint. So that's why HTTPS is super important.
Okay, cool. So definitely a lot of other questions. We'll definitely try and answer them on the comments thread after the event. And so want to thank everybody for your time. And Matt, just hand it back to you to wrap us up.
Thanks, Kamran. So it looks like we're up against our hour time slot, as Kamran mentioned. We'll do our best to address any questions we didn't get to in the panel there in the comments thread. YouTube will archive the video of this live panel, and it will be available on this event page shortly. And we will also post a link to the slides that we shared today. So thanks again, everyone, for coming to view us today. We had close to a couple hundred viewers, so this appears to be a topic of great interest. And as Kamran mentioned too, if there are any particular aspects that you'd like more in-depth discussion of, please mention them in the comments, and we will take that into consideration. So for Kamran, Andrew, Felix, James, and Karthik, I think that'll do it for us today. Thanks everyone very much for attending, and have a great day.
Thanks, guys.